this video we're going to explain the process to translate or to go from a finite state machine and build a digital circuit. Now, in order to explain this process, we are going to start from our generic finite state machine that has 4 states: 0, 0, 0, 1, 1, 1, and 1, 0, and it has the following transition structure. Now, this transition structure is assuming that the machine has 2 variables to represent the state, but also 1 input. And the input values that are considered for all these transitions are shown here. So this is our starting point, a fully specified finite state machine. Now, aside from 1 input, which we're going to call I, we also have the state of the final state machine that we're going to represent with 2 bits, S0 and S1. As we can see here, we have 2 bits. Now, from this description, we can derive the truth table in which I, S0, and S1 are used to compute the values S0 plus and S1 plus, denoting the next states to which the machine is making a transition. Since we have 3 Boolean variables here, we need to write 8 combinations: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, and finally 1, 1, 1. So these are the 8 possible situations when we consider input and current state. And now we have to derive the values of the next state. And we derive this simply by looking at this diagram. We know that from state 0, 0, when it comes to 0, we make a transition to the same state. When we are in state 0, 1, and we have a transition 0, we go to state 1, 1. 1, 0 with a 0 makes a transition to 0, 0. 1, 1 with a 0 remains in the same state. 0, 0 with a 1 makes a transition to 0, 1. 0, 1 with a 1 remains in the same state. 1, 0 with a 1 remains in the same state. And finally, 1, 1 with a 1 makes a transition to 1, 0. So what we have here basically is the truth table for 2 Boolean variables, S0 plus and S1 plus. Now, the trick to implement a digital circuit from here is simply to implement these 2 Boolean functions as if they were regular Boolean functions. In other words, taking the input I and S0 and S1, we build a set of logic gates. Okay, this will be logic gates that produce as output precisely this column of the truth table, SO plus. And we're going to have another set of logic gates that, with the same inputs, in other words, the inputs and the state variables, they produce S1 plus. Now, here comes the final touch to make sure we implement this finite state machine. These 2 variables here, or these 2 functions, what are telling us is the values that should be the future state, or the state at the next time unit. So these 2 signals will be stored in a flip-flop, a 2-bit flip-flop, which is going to hold the current state. We can denote this like this with a clock signal. And as we can see, the output of these 2 logic blocks, it's being now captured and stored. Another way of looking at it is that this is an element that has memory, and it's captured as the current state of the machine. Now when the clock signal makes a transition, the future state of the machine becomes the current state of the machine. And therefore what we have here is precisely the value of S1 and S0, and therefore they need to be connected to S1 over here and to S0 over here. Now this is the resulting implementation of this finite state machine. So we have seen the transition from this diagram to a circuit, but of course we need to implement with gates these two columns over here. Now suppose that we need to implement also some values for certain outputs, and let's suppose that the outputs of the circuit are only dependent on the state variables. Now we have four states, 0, 0, 0, 1, 1, 0, 1, 1, and let's assume we are extending our finite state machine. Let's assume that we have two outputs, O0 and O1, that depend only on the value of the states. And let's just write some arbitrary logic here. This would be the value of one of the outputs depending on the states, and this would be the value of the other output. Now one more observation before we proceed. Since the outputs only depend on the value of the current state, this is what is called a Moore machine. How would we implement this? Well, it's very simple. We just need to implement a Boolean function that gives us this truth table, which just so happens to be, if I take this signal, and this signal is actually an XOR gate, this will give me output O0, and in this case, if we look at this truth table, is actually an AND gate. This will give us O1. So another way of looking at this diagram is the following. In general, for a Moore machine, what we're going to have is the inputs going into a set of logic gates, and by this box now I'm lumping together these two. In other words, this would be the block named now logic gates. This block would be in charge of generating all the required signals and signals, whatever is necessary, that feed into a memory element, which obviously has a clock, which will contain the state. And the value of these variables is also used by these logic gates to compute the next state. Additionally, in case of a Moore machine, there is another block of logic gates here that take the state variables and produce the outputs. So what we have here is an schematic representation of a Moore machine. Now what happens if what we have is a Mealy machine? In the case of a Mealy machine, is very similar. In this case, the outputs O0 and O1 wouldn't depend only on the state variables, but would depend on the state variables and the inputs. In other words, these three variables will be taken into account to compute the value over here. But again, we are in a similar situation. We have two Boolean functions that can be implemented with a set of gates and produce the proper truth table. The equivalent schematic for a Mealy machine would be the following. I still have my inputs of the Mealy machine. These inputs go into a set of logic gates. These logic gates still produce a set of signals that represent the state, and this state feeds back in here. But now this logic block is more complex and also produces another set of signals, which are the outputs. In other words, in a Mealy machine, all the logic gates that are connected to the states actually produce two sets of outputs. the state outputs, which would be represented by these columns here, and the outputs, which would correspond to these two columns over here. So this scheme here corresponds with the structure of a Mealy machine.